Now we'll look at some common definitions and relationships among the terms that are used to qualitatively describe acidic and basic aqueous solutions. Firstly, you have the pretty well-known pH term. pH term is a mathematical definition for the concentration of hydronium cation in a solution, or simply hydrogen ion. It's the negative log of the hydronium concentration, or the negative log, more frequently just written as negative log of H+. That is the H in pH. P stands for power. You don't see an explicit power in this form of the formula. So, to derive such a power, you want to get rid of the logarithmic term. So I'll just copy that for H+. We'll bring the negative to the left side of this equation as written. And then we'll take the mathematical antilog of log base 10, which is understood when someone writes merely log. So 10 to both sides. The antilog eliminates the log, and you have the concentration of H+, or H3O+, in solution of an aqueous solution is just 10 to the negative of whatever the pH reading is. There's the power of H, really the power of H+. So for example, in a neutral water solution, the concentration of H+, as you've seen, at equilibrium is 10 to the minus 7 molar, and that equals 10 to the minus pH, and you can see that the negative 7 and the negative pH match. Therefore, the pH would be 7 for a neutral water solution. Similarly, we could define pOH, or P anything, as the negative log of the concentration of something, or that actual term. So negative log of the hydroxide concentration, usually at equilibrium, will be the pOH, and therefore in terms of exponents or power of hydroxide, the concentration of hydroxide is 10 to the minus pOH. You must never write P as a capital. P is a lowercase, and that is a strict convention. Oftentimes, equilibrium constant values for acids, Ka of some acid Ha, or Kb of some base A-, oftentimes the numbers are incredibly small, so we want the convenient pKa term. So pKa of an acid Ha is just negative log of the equilibrium constant value, often called the ionization constant for that acid, and pKb will be negative log of Kb. A convenient and interesting relationship emerges when you look at aqueous solutions at 25 Celsius or 298 Kelvin, and that is the autoionization constant of water, which is concentration hydronium, or just abbreviated H+, times concentration of hydroxide at equilibrium. If you take the negative log of each side of that equation, negative log Kw, negative log of this product, and then because you have a product of these two numbers, you can just, using logs, write them as two separate logs as a sum, negative log concentration H+, plus negative log concentration OH- equals negative log Kw. But by definition of this P term, this is just pKw, and this is pH, and this is pOH. And since Kw at 298 Kelvin is the negative log of 1 times 10 to the minus 14, if we want to use 3 sig figs. The negative log of 10 to the minus 14 is 14. So that means if you know the pH of a given solution, aqueous solution at 298 Kelvin, you automatically know the pOH, because the sum of the pH and the pOH have to add up to the simple number 14, which really shows the benefit of expressing these values in terms of P, or powers, or logs. So for example, at equilibrium, if you know the pH of a solution is 3.4, then the pOH is just going to be 14.0 minus 3.4, which is 10.6. And then if you need the hydroxide concentration at that pH of 3.4, well, we know by definition it's 10 to the minus pOH. So that's 10 to the negative 10.6 power. Molar, which is a number. You don't have to do anything else to that number. You could put it in your calculator and express it in more standard scientific notation, but you don't have to unless you're explicitly asked to do so. Similarly, the hydronium or H plus concentration at a pH of 3.4 is 10 to the negative 3.4 molar. Another convenient relationship to establish, we've seen that Kw equals Ka of an acid HA times the equilibrium constant Kb of that specific acid's conjugate base, A minus. So again, we take the negative log of both sides, Ka of the acid times Kb of its conjugate base, and we get pKw. Here I'm going to express that product as the sum of two separate logs. There's the sum, and the negative sign multiplies out. Kb of A minus. But this term, just by definition, negative log Ka, is just simply the pKa of HA, and the negative log of Kb of A minus is the pKb of A minus. And at 298 Kelvin, pKw is 14.0. So if you know the Ka of an acid HA, then you also know its pKa, and you know the pKb of its conjugate base because they have to add up to 14.0. So for example, if you know that the equilibrium ionization constant for the acid HA, we'll make it a super easy number, 1.00 times 10 to the minus 3 in value. Well, the pKa is the negative log of that number. It's just going to be 3. Negative log of 10 to the minus 3 is 3 because of the negative in front of that. So we'll make that 3 sig figs. So that would mean that the pKb is 14 minus the pKa at standard temperature, and the pKb would be 11. And that means the Kb would be 10 to the minus pKb, or 1 times 10 to the minus 11, which is incredibly small. So you can see, even though this acid is weak, with a Ka of 10 to the minus 3, its conjugate base, A minus, is even weaker. Notice that I'm not putting molarity or anything after the K values because the equilibrium constant values are unitless. So these formulas are very important and frequently used, relating pKw, pKa, and pKb of a conjugate pair for a reaction, and also pKw to pH and pOH. Again, this is all for aqueous solutions. So this P, or power convention, is really just a convenience, and it's just a definition so that we can use small countable numbers. You can define anything as a P. P smiley face is the negative log of smiley face, whatever function that would be. But remember, make that P relatively small. It's extremely important that you see the pattern to pH, pOH, or P anything, relating the concentration in molarity of hydronium cation and hydroxide anion to the P values. So it's important to practice this chart. I'll give you some simple pH values and pOH values, and we'll check out the concentrations to, let's say, the 10th place before the scientific notation. So simply put, for pH of, let's say, 7, that means the concentration of hydronium is 1 times 10 to the minus 7 molar. The molarity is right at the top of the column. And at room temperature, the product of the hydronium and hydroxide concentrations has to be 1.0 times 10 to the minus 14. So that gives you the hydroxide, and the pOH would also be 7. Further, pH plus pOH adds up to 14. Let's try a pH of 3. That would give you a concentration of hydronium of 1.0 times 10 to the minus 3 molar. Because the pH is 3, the pOH would be 11, and so the concentration of hydroxide would be 1.0 times 10 to the minus 11 molar. All solutions below a pH of 7 are acidic, and all solutions above a pH of 7 are considered relatively basic. If we look at a pH of 6 in the acidic range, that's still a very small molarity or concentration of hydronium. It's 1/1,000,000th molar, but you could see that there is a 10 times or a 10-fold increase in hydronium concentration. So 1 pH unit change is a 10-fold change in hydronium concentration. And the confusing thing for most people is that as the pH goes down 1 unit, the concentration goes up or increases by 10. So if the pH went down by 2 units, let's say from 7, then the concentration of hydronium at a pH of 5 is 1.0 times 10 to the minus 5 molar. There would be a 100-fold increase in acidity in hydronium concentration, though the pH dropped merely, it seems like a little bit, but it's actually a lot, 2 pH units. And then to complete the chart here, we have 9 for the pOH when the pH is 5, and 8 is the pOH when the pH is 6. And then you could just complete the pattern here. 1.0 times 10 to the minus 8 and 1.0 times 10 to the minus 9 molar, as you see respectively. Let's look at a couple of basic numbers, and then we're going to look at some very, very important benchmarks between pH units that you're going to use so that you no longer will need a calculator to get an excellent approximation of molarity based on pH, molarity of the hydronium. So here we have an even smaller concentration of hydronium, 10 to the minus 8, but we have a pOH of 6. So now in basic solutions the hydroxide concentration is increasing. Let's try 12. So the hydronium concentration is now trillionth molar, unbelievably small in very basic solutions. Hydroxide, the pOH is 2.0, so the hydroxide concentration is now just 1/100th molar, 10 to the minus 2. I'm going to focus now on some pH values to the 10th place just between any two pH units, so you can get some benchmarks as far as the molarities. So for pH of 9, we have a molarity of hydronium of 1.0 times 10 to the 1.0 times 10 to the minus 9 molar. I would like to know, when the pH is 8.5, halfway between 8 and 9, what happens to the numbers? The first thing to see is that we can consider a pH of 8 as a concentration of hydronium. Instead of 1 times 10 to the minus 8, I can write the equivalent of 10 times 10 to the minus 9. So that you could see between pH of 9 and 8 that the concentration of hydronium goes from 1 times 10 to the minus 9 molar to 10 times 10 to the minus 9 molar. So most people are going to say, oh, at halfway through, that's got to be, half the concentration at pH of 8. But that is wrong. Don't bother writing that. You know that the concentration of H plus here is 10 to the negative pH, which is 10 to the minus 8.5. So that's correct, but that's not going to help us get our benchmarks. If you put that in your calculator, you will see that the pH is 3.2 times 10 to the minus 9. So the 3 is good enough for us to get our benchmark here. So it's about 3 times 10 to the minus 9 molar. So when you go from a higher pH value to halfway between the next lowest pH value, the number in front of the exponential term goes just from 1 to 3. So it doesn't go from 1 to 5, it just goes up from 1 to 3. We need two other benchmarks. I'm going to take one at 8.3, and we'll have another one at 8.8, so that we can get two other numbers. This way we'll at least be able to a very good degree approximate to the 10th place practically what the concentration will be, and we'll also be able to put in the correct exponent. Now remember, when you see a pH of 8, the exponent is going to be a 9 with a negative in front of it. So if you had a pH of 4.5, you'd better see something times 10 to the minus 5. Or if the pH is 1.2, you'd better see something times 10 to the minus 2 molar. So the pattern never fails. So to get the concentration of hydronium at a pH of 8.3, I put into the calculator 10 to the minus pH, or 10 to the negative 8.3, and now I get very close to 5.0 times 10 to the minus 9 molar. So we have a nice little connection here. When the pH is something 0.5, we start writing the concentration with 3. When it's something 0.3, we start writing the concentration with a 5. So there's a 5-3-3-5 switch. You should practice that and get used to that pattern. Now let's put in 10 to the negative 8.8. 8.8 is the pH value, and we'll see what concentration we get for that. We actually don't have to punch it into the calculator. There's a 1 here, there's a 3 here, so I'm going to take a guess that it's 2, and that guess cannot be far off. We're just approximating here. It works out that that's 1.6 times 10 to the minus 9. But since 8.3 is just 0.2 pH units below 8.5, if I use 8.7 as the other benchmark, and you put in 10 to the negative 8.7, you get 2.0 times 10 to the minus 9. So that's a more accurate benchmark to use. So keep this in mind when you're going from pH to concentration. You now have a very, very powerful approximator And you do not have to use your calculator, and you cannot use your calculator on a more complex pH problem on a multiple choice question. So you can complete the chart on pOH values here. pH of 9 would give you a pOH of 5 and a hydroxide concentration of 1 times 10 to the minus 5. pH 8.3 would give you pOH 5.7. pH 8.5 would give you pOH 5.5, and pH 8.7 would give you pOH 5.3. So if you needed the hydroxide concentrations, respectively, of 5.7, 5.5, 5.3, you just take 10 to the minus 5.7, etc., to get the values. Or you could use the benchmarks that we've seen here, that at a pOH of 5.3, we see the 0.3, so we start to write 5.0, and we have 5.0 times 10 to the minus 6 molar hydroxide. And then we can continue with the benchmarks. Here we're going kind of upside down because we're going from a higher pOH value, a lower pOH value to a higher pOH value. But you can see that this works out beautifully without the need of a calculator once you get this down. For now, you could check this if you type into your calculator 10 to the negative 5.7, 10 to the minus pOH, you will get a hydroxide concentration of 2.0 times 10 to the minus 6 molar. So it works. So practice this, try several random pH units and get the benchmark values between them until you can throw your calculator away for pH calculations.